All right, welcome back. In this section, we are going to look at nonlinearities. And so far, models that we've looked at can be described approximately by linear time invariant differential equations. We assumed that the models were linear. In this section, we are going to define the term linear and nonlinear and how to differentiate between the two. So, by definition, we can say that a system that is linear is a system that has two fundamental properties, that is, superposition and homogeneity. And the property of superposition means that the output response of a system to the sum of the input is the sum of the response to the individual to the individual inputs. What that statement means is, if we have an input into a system of our input is x1 and the output is y1, and we input again into the system x2 and we produce y2. If we combine the two inputs and put it back into the system such that x1 plus x2, we must produce y1 plus y2. If that happens, then the system is linear. The property of homogeneity describes the response of the system to a multiplication of an input by a scalar, meaning that multiplication of an input by a scalar should yield a response that is multiplied by the same scalar. So, if our system here, our input is x1 and our output is y1, if we multiply this by a scalar alpha, and then our output should be also scaled by an alpha. If this property holds, then the system is linear. We can visualize linearity as shown in these two figures, A and B. And we can see that in figure A is a linear system where the output is always half the input. And this figure satisfies both linear system properties. If our input is 1, for example here, then we know that our output is going to be a half. If the input is 2, then the output is going to be 1. So let's test the linearity and superposition on this diagram. Using superposition, an input of 1 and 2 will yield an output that is the sum of the two individual, meaning that using superposition, if we input is 1, then the output will be a half. If the input is 2, then the output will be 2, meaning that, so our input here was x1, this is x2. So x1 plus x2 should yield y1 plus y2. So x1 here was 1 plus x2 was 2, and y1 we can say is a half, y2 was 1, meaning that we had x1 plus x2 is 3, and which implies that we should get y1 plus y2 should give us 1.5. So we can say that x1 plus x2 was 3, which is here, and this should give us around 1.5. So, meaning that it satisfies superposition. What about homogeneity? Using the homogeneity, if the input is 2, if we input 2 here, If our input is 2, then we know that our output is 1. So with homogeneity, what we want is we want to scale. So meaning that if I double this such that our input now is 4, which is here, the output should also double, meaning the output should be 2. If we line this one up, we can say that when you are at 4, then the output is double, which is 2. Meaning that this part, our first diagram, this is linear. It satisfies the linearity property. Our second diagram, as we can see, it does not confirm or comply with the linearity property, because if we take, for example, our input is 1, our output, let's assume that maybe this is 1.5. If you are at 2, maybe we say this is it's closer to, maybe we can say it's maybe 1.8. Now at 3 should give us the sum of this, which should be around 3.3, and we are nowhere near around 3, etc. We are not even above 2. Okay, so meaning that this is not linear. A common application or a common nonlinearity, physical nonlinearities of certain behavior is found in amplifier saturation, whereby the output increases with input initially and beyond a particular value. For example, here it increases and beyond this particular value, and the output remain constant. It's like it's saturated. So, and a classical example for this is found in amplifiers and also magnets. They have this type of nonlinearity behavior. Another one as well is the dead zone, or also called the threshold. A threshold. It means that the output is 0, so the output, nothing happens up to there, is 0 for a small value of input. Then the output is available only when the input has increased beyond a particular threshold. So if you pass a certain threshold, then the input will increase. And you'll see mainly this behavior in motors, when you supply a small little voltage to a motor and the motor will not respond at that time. Or also with diodes as well, the diodes, they have this type of behavior. And another nonlinearity is the backlash of the gears, whereby gear meshes together in between, because they are really not touching. You have certain friction, and when the gear is turning, the first gear can start turning before it touches the other gear. For example, let me see if I can draw a gear here. My drawing is going to be very, very bad. And let's say you have a bigger gear here, maybe. Let's say this one is in there. So this gap, the gap in between there, when this gear start turning, this gear will move first before this start moving. So for some reason, you will have something called a backlash, and it has some nonlinearity properties. Now, when we have these nonlinearity properties, what we normally do is we need to linearize the system. So the electrical and mechanical system covered so far were assumed to be linear. However, if any nonlinear components are present, we must linearize the system before we can find the transfer function. So in this part, we'll show how to obtain a linear approximation to a nonlinear system in order to obtain a transfer function. And the idea is you want to pick a particular point, for example this point here, and if we draw a tangent line there between in this small little region, this will act as if it's a straight line. Whenever you have a straight line, then you can take that small little portion as linear. You can do another one here, draw another tangent line, you can do another one here, draw another tangent line, do another one here, do another tangent line, etc., etc. So meaning that we are just taking some small portion, the difference between x minus x naught, that small perturbation, and we that small little movement that's what we are trying to linearize around, because you don't want to take a bigger portion whereby if you say, okay, I'm going to take maybe a point between here and there, all right, it's very, very difficult because you have all this part, and that part is really nonlinear. So what you want to do is you want to pick a smaller point, and the first step is you have to recognize the nonlinear component and write down the nonlinear differential equation. Then find an operating point. An operating point will be x naught and u naught. And once we found the operating point, and we are going to linearize the nonlinear system using the Taylor series expansions. Then we are going to substitute the linearized terms, and we'll take on from there. So let me look at an example quickly so that we will look at the procedure. So we are given this equation to linearize it around x is equal to 0. So I'm going to write certain procedures, and I hope they will be helpful in solving the rest of the sections. So step 1. First, what you want to do is you want to find the equilibrium point and the equilibrium equation by setting all the derivatives to 0. So let me write that. So if I rewrite this equation, we have x double dot plus 3x dot plus 2x is equal to sine x. We want to find the equilibrium point and set the equilibrium equation by setting the time derivatives to 0. So this is a time derivative. We want to set that one to 0. This also is time derivatives. We want to set that one also to 0. Meaning that what I've done is I just took x double dot is equal to x dot, which is equal to 0. So what I've left with is we have 2x is equal to sine of x, or I can write as 2x minus sine of x is equal to 0. That's the first part. The second part, step 2, we want to write down the perturbed equation by perturbing all the variables about the equilibrium point. All it means that is we want to write down an equation that is going to disturb we are going to disturb the equation or the system a little bit, or shift it just a small little bit at a certain point. Let me just write down step 2. So we want to write down the perturbed equations by perturbing all the variables about the equilibrium point. It means that what we want is we want to set x is equal to x naught plus some delta x. Meaning that we want to disturb around this area just a small little bit, which implies that our delta x, the small little movement that we want, is x, our x point, minus something that is very small in the neighborhood. That's all that we want. So hence we can substitute this into our original equation. So substitute the perturbed variable into the original differential equation. We are going to have x dot dot x naught plus delta x dot dot plus 3x naught dot plus delta x dot plus 2x naught plus delta x is equal to sine of x naught plus delta x. So what I've done is I've just substituted for x is equal to x naught plus delta x. Alright, if you had a x dot dot, so you have the x dot dot, you just had a x dot dot there, and so on and so on. Now looking at this equation, we said that we set our derivatives to 0 from here. We set our derivatives to 0, meaning that that's 0 and that one was also 0. So let me rewrite this equation. So we are going to have delta x double dot plus 3 delta x dot plus and we say also x naught was also 0, because this is the point that we want to find our equilibrium at. So 2x naught is 0, so I can disregard that. So we have 2 delta x is equal to sine x naught is 0, so we are going to have sine delta x. And I can rewrite this. I just want the sine x to be in the inside, so I'll have delta x dot dot plus 3 delta x dot plus 2 delta x minus sine of delta x is equal to 0. Now you can see that this is our nonlinear part. So this is that's our nonlinear part, and that's the part that we want to linearize. So step 3, linearize the nonlinear terms using Taylor's expansion. Now Taylor's expansion, let me just write down the Taylor's expansion here. We have, I'll write it in a different color. We have a function which is equal to fx naught plus partial derivative of that function and evaluating it at x is equal to x naught times x minus x naught over 1 factorial plus x minus x naught squared over 2 factorial plus dot dot dot, and so on and so on. So what we want to do is, with Taylor's expansion, we don't really care much about the higher order terms. If we approximate it using our first derivative up to here, we will be okay. Okay, so those are higher order terms, we don't really care about them. So I'm going to rewrite this equation, then we are going to use it to linearize our nonlinear part. So this will be, and I can bring this one on this side, minus fx naught is approximately of this. So far, even though this is a single variable, you can just write it as a derivative, but I'm going to use the partial derivative of it, because in the near future you'll see a lot of variables, but the procedure is exactly the same. In here, the function that we had, the function that we want to linearize, f of x, is sine of x minus sine of x naught is approximately. Now we want to differentiate. So to differentiate a sine function with respect to x, we are going to have our cosine of x and we are saying that we are evaluating x is equal to x naught, which is equal to 0, and which will just give us 1, and meaning that here we are having 1, and this part, if you can see from here, we called it delta x. So I can just say delta x, x minus x naught. So, and we say x naught is 0, so this is 0, meaning that we have a sine of x is approximately delta x, and we know that sine of delta x, our sine function here was the nonlinear part, and what we can do, I forgot a delta x here, apology. So this is sine delta x. So yeah, we have it here. So now what we can do is we can substitute this linearized part into our equation. So let's rewrite that equation again. We had delta x dot dot plus 3 delta x dot plus 2 delta x minus sine delta x was equal to 0. So what we want is we want to substitute this into there. And so step 4. So step 4, it says that substitute the linearized term in the perturbed equation. So when we do that, when we substitute the sine of delta x into the equation, we are going to have delta x double dot plus 3 delta x dot plus 2 delta x minus delta x. Now we are writing the delta x instead of sine delta x, because we say sine delta x is equal to delta x is equal to 0, and we can simplify this as delta x dot dot plus 3 delta x dot, and 2 delta x minus delta x will give us delta plus delta x. So plus delta x is equal to 0. So this is our final answer. And as you can see, it does not contain any nonlinear terms.